Okay, this video is a introduction to a very important topic in computer science called recursion. And so you might be thinking, well, what exactly do I mean by recursion? You know, funny graphics aside and so on. What is recursion? Well, simply put, recursion is when a method calls itself. So we've already seen that in Java you can have static methods, and the static methods can call other methods if they want. You might be surprised to learn, instead of like method A calling method B and then method B calling method C, you could have method A call method A, and that call to method A may call method A again. To the computer it's just the same, whether it's calling a method by a different name or the same method repeatedly, though it's a bit confusing at first, but it's a new way of addressing problems in computer science. We're going to talk a little today about the divide and conquer concept in computer science, so breaking a problem up into smaller pieces and then solving the smaller pieces and then putting them back together. Recursion is a very powerful programming paradigm. Things that would be difficult to do without recursion can become quite easy and quite elegant, and you can write complicated algorithms in a small amount of code. So it's really worth getting through the initial confusion and getting your head around how recursion works. And we'll look at first off how it's related to a mathematical concept. If you've done some mathematics, you may have heard of mathematical induction, and I'll show you a little bit about that. And then we'll go through some example applications like Factorial, searching for a number in a sorted list, a famous algorithm called binary search, and then we'll draw some pretty graphics. And then we won't be doing any sorting in this lecture, but we'll look at a sorting algorithm that uses recursion next time. So first of all, how is it related to mathematical induction? This is kind of like dominoes. If you can solve it for a problem of size n-1, then that solves it, you know, for n. So if you start at a small case, then basically if you can solve the small case and you know you can go from that small case to one bigger, then you can solve the one bigger problem. And if you can go from the one bigger to one bigger than that, you can eventually reach any integer n you want. It's just a matter of repeatedly applying this induction step. And we'll use similar terminology when we're talking about recursive algorithms in computer science. There's a base case, so this is a small value of n, normally something like 0 or 1. And from that base case we're going to have an induction step. So we're going to go from a smaller problem to a slightly bigger problem, something from size n-1 to size n. Here is a formula for computing. So say you want to sum the numbers from 1 up to including n. One way you could do that is, you could just write a computer program loop overall. You could have a for loop going from I equals 1 up, strictly less than or equal to n, and then sum all the numbers up. But you don't really need to do that, because mathematicians know there's a closed form solution for this sum series from 1 up to n, and it's shown right here. It's n times n plus 1 divided by 2, and that's true for any integer value of n. But how do they know that? How do they know for any value of n that's actually true? Well, you can prove that using induction. And the way it works is you first start off with your base case. In this case, we'll take a base case of n equals 1. And can we show it's true for the sum of all integers from 1 up to and including 1? Well, what's the sum of all integers from 1 up to including 1? Well, that's just 1. Alright, so we know the answer. The sum of those integers is actually 1. Alright. Is that the same as the formula? Then the formula is n times n plus 1 over 2. Well, if we plug n equals 1 into there, you get this formula, and you can see 1 times 2 divided by 2, well, that's 1. So 1 equals 1, that's a true statement. So the base case is true. Now the induction step, this is where we need to go from a smaller problem to a slightly bigger problem. And we're going to assume we can solve that smaller problem and see can we show that it holds for that larger problem. And if we take the sum of all numbers from up to and including n, you can see in the blue here the numbers 1 up to including n minus 1 is our smaller case. That's what we're going to assume is true in mathematical induction. We assume that sum from 1 up to n minus 1 is equal to the stated formula. All right, but this formula was in terms of n, and what we have here is n minus 1. So instead of using n in this formula, we plug in n minus 1. So we plug in an n minus 1 here and n minus 1 right here. Okay, and that gives you n minus 1 plus 1, that just gives you the n, and then divided by 2. We're assuming this blue part is true. And what do we have left over? We just have the n hanging on the end. We can multiply the numerator and denominator by 2, and then simplify this expression. We can put the n on the inside with the n minus 1. All right, and n minus 1 plus 2, you get n plus 1 times n over 2. So you've shown what we wanted to show, which was that it was true for n. So given that smaller case n minus 1, we were able to go to the larger case, and therefore we could start at our base case of t of 1, and then we know it's true for t of 2, and if it's true for t of 2, we can go to t of 3, and then we can just iterate and prove it for all n. Okay, so enough mathematics. Let's have a look at recursion in the Java programming language. And sort of hello world for recursion is computing a factorial. And if you don't remember factorial, something like n factorial up here is the multiplication of all the numbers from 1 up to n. We've got a base case, as in induction. The base case of 0 factorial is equal to 1. And the algorithm is similar in spirit to mathematical induction. We're going to assume we know the answer for n minus 1. If we knew what n minus 1 factorial is, well, what's n factorial? Well, we just have to take that n minus 1 factorial and multiply it by n. And you can actually see that in the code. Here's the Java code that computes factorial recursively. Here's our base case. If n equals 0, return 1. So if we're trying to compute the factorial of 0, then the answer is 1. If that's not the case, right, and recall a return statement is terminal for a method. So we hit this return 1 and it's over. So if n was equal to 0, we just return 1, and then the fact method is all done and dusted. If it wasn't equal to 0, then what do we say? Well, I don't know what the factorial is, but if I knew the factorial of n minus 1 and I multiplied by n, that would be the answer. And that's it. There's your algorithm for computing factorial. And the second line is what we're calling the induction step. And we can pull it up here in, let me pull it up in Eclipse. And here's the program. And I can, we can put in an argument like 5, run it, and we'll get 5 factorial equals 120. All right. The flow of control here, though, is a little confusing. We read in the integer in the main program, and then we're going to call fact with that number. All right, in this case 5. The factorial method is going to fire up with n equals to 5. It's then going to call itself with n minus 1. So it's going to call the fact. The first call to fact is actually going to call fact again, and then that fact is going to call it again, and so on. And so let's go ahead and run that in the debugger. We can trace its execution. Alright, we've started up. We're just reading in the command line argument. Command line argument is 5, and I'm going to step into this. Here's the first instance of factorial, and notice the parameter value n is 5. And step over, and then it's going to call factorial, alright, but it's going to do it with a 1 less than. And you can actually see up here in this stack trace up here, you can see we were running the main program, and then we started to run the factorial method, and now we're running another version of the factorial method, and now the n is down to 4. Alright, step over, we'll step into that, and now there's another instance of factorial with an n equals 3, another instance with an n equals 2, another one with an n equals 1, and then oops, I didn't step into that one, so you didn't get to see it. But that last one ran the base case and then returned 1. And now it's going to back out of all those, and as it does that, it's going to actually calculate that factorial. And if it prints, I get 120. So this fact method, when you're calling yourself recursively, it keeps calling itself until at some point it reaches the base case, and then it returns from that base case and then uses the answer 1 to multiply by n, and then it takes that answer and then passes it back to the person that called it, and so on until it backs its way all the way out. Alright, we seem to have jumped quite a few slides ahead here. Let's get back to where we were. Okay, and here's an instrumented version. I can show you in the slide. So all I've done is added print line statements to the beginning of fact and to the base case, and then to printing out stuff right before it exits. If I did the factorial of 4 instead of 5, it would fire up print start fact 4. It would skip the base case and then call itself recursively. So the next thing you see print is that fact with a parameter of 3 do its println, and then that factorial doesn't hit the base case, prints fact 2, then it calls itself and prints fact 1. Alright, at this point it calls itself with fact 0, and that's the base case. So that very last call to fact falls into this if block, prints out n base fact 0 and returns 1. At this point, that other one, alright, the factorial that was called with a parameter of 1 now fires back up, gets that 1 return result, and uses that in the step variable. And then it can go ahead and print out the end fact 1, and then as you see it starts to back its way out, and eventually all levels of the fact method have completed, and then the main program goes ahead and prints the actual factorial. Do you have to do it this way? Would you really necessarily, I mean, if I asked you to do factorial, would you really have done it this way? Probably not. You're more likely to have done it with the algorithm on the right. This is a simple iterative algorithm. You give it the integer n you're trying to compute the factorial of, and it just loops over and multiplies the result value of all those numbers from 1 up to n. There's always an iterative version. There's no reason you have to solve this problem or any problem with recursion, but there are good reasons you might prefer to solve it with recursion. Often the case, and you can even see it in the factorial here, the recursive algorithm is often more compact and easier to understand. Maybe not, maybe this isn't easier at first, but once you get your head around it, this is actually shorter and arguably easier to understand. And as you look at more and more complicated algorithms, it actually gets a lot easier if you do a recursive solution than if you do an iterative one. It's easier to reason about whether it's correct or not because you can use sort of like an inductive argument. If you can show it's true for the base case, and you can show each step in the recursive algorithm is correct, then you know the whole thing is correct. We're going to look at the end of the lecture reasons not to use recursion, and I'll show you a problem where using recursion leads to spectacularly bad performance. And another reason not to use it is on very low power processors. So something like an 8051, this is a microcontroller. It has 128 bytes of memory. That's not a lot of memory, and actually calling yourself recursively has some amount of overhead. On a modern desktop computer, it really isn't going to be a problem. But if you're running, you're making a program for your microwave, you probably don't want to use recursion. We didn't really need it for factorial, right? But let me show you another example. This is a famous algorithm, a search algorithm called binary search. The idea of binary search is somebody has given you an array of sorted numbers or sorted names or something that has a sorted order. Your job is to see if you can locate a certain number or say a person's name in a telephone book or something like that. You want to see, do they exist in the list or do they not? The most obvious way to do this, right, is just to look at the first one and say, is it the first one? No. Then go on to the second one. Is it the second one? No. And then go on to the third one. And work your way all the way through and see if it's anywhere in that list. This is not obviously the smartest way to do it, especially, and remember, these are sorted. That's the key. They must be sorted. If these numbers are just, jumbled together in no particular order, then you're going to have to, go one at a time. But if they're sorted, it would be sort of like opening that phone book and you're looking for, somebody's last name starts with T, and then starting in the A's and comparing every name on the A page and then going to the next page and working your way through the B's and the C's and so on. It's just not a very smart way to play the game, is it? And in computer science, often we use what's called the big O notation. This is worst case behavior. If we had a list and it had n items, in the worst case, going linearly through the list is going to take n operations. You're going to have a for loop that loops around n times. So it's big O, and worst case performance is on the order of the number of things in the list. This is not binary search. This is the dumb way to do it, linear search. Binary search is just like playing higher or lower. So if somebody says, I'm thinking a number between 1 and 100, what should you guess? Well, you probably should start around 50. And then if I say it's higher, you're gonna bisect that range from 50 to 100, guess 75, and then half the range again, 63 if I say lower, and then I say higher, then I say higher, and then then you guess the correct number. That's essentially what binary search does. Given an array that's in sorted order, what binary search does is first calculate the midpoint. Given how many things are in it, it finds that middle point, and first thing it does is says, all right, is this middle element of my array what I'm looking for? We've got some target value, in this case 5. We've got a low index, this is 0, and a high index 10. So we've got, how many things we got in the array? Well, we have 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Low index 0, high index 10. To calculate the midpoint, what did we do? Well, we added 0 plus 10 and divided by 2. And remember, if both things on both sides of the slash are integers, it's going to do integer division. So we're going to get 5, not 5.0. We're not going to get a floating point value. In this case, it comes out even, but if it had been like 11 divided by 2, it still would have come out as 5 in integer land, which is fine for this algorithm. We divide it by 2, and we first see, is 9 equal to 5? No. Well, where should we search? Well, if we're looking for the target value of 5 and we hit a 9, it's obviously on the left side. We adjust our low index. All right, we leave the low index alone at 0, but we bring the high index to 1 less than the 1. We already compared 9, so there's no sense in checking that array element again. Compute a new range, 0 to 4, find the midpoint of that by adding 0 plus 4 divided by 2. Is 2 what we're looking for? Alright, well no, we're looking for a target value of 5. But where should we look? Well, we want to look in the upper half. Now we set the low value equal to 1 more than what that midpoint was, and calculate a new midpoint. Alright, and that midpoint is 3 plus 4 divided by 2, or 3. And yep, there we got it. The midpoint is the target, and therefore we're going to say yes to the question, is 5 in this sorted array? How do you do this? Well, it's quite easy to do if you do it recursively, and here's the recursive algorithm to implement that. First, let's just have a look at main. So main sets up an array, and it's a sorted array. I've got even duplicates. I've got 2 2s. We've got gaps in the sequence. And the user of this program is going to input a number, and then it's going to determine, did it find this number or not. It's going to print out, whether true or false. The static method binary search, it returns a Boolean, true if it found it, false otherwise. It takes a target value, and it takes a low and a high. So just in the slides I just showed you, the low and the high index of the array, and then it takes a parameter D, which is that array containing the data. When we initialize it down here in the main program, we're going to start the low value to the smallest index in the array, the high value to the highest value, right? And remember, since we count from 0 in computer science, the highest element is the length of the array minus 1. We calculate the midpoint. We just print out some informational stuff so we can see what the algorithm is up to. We see, is the midpoint equal to the target? If so, print or return true. We've found it. If high is less than low, this is a failure case. If that circumstance ever happens, then we've searched and we're unsuccessful, so we return false. If what we're looking for, if the midpoint is less than the target, then what we need to do, well, we got to search on the other side. So we set the low equal to the midpoint plus 1 and the high point equal to the current high point, and then search that. Else we research the low end. So this is the recursive set. These are the base cases. If we found it, great. If we failed to find it, well, we're done. You must always have such base cases in recursion. You can't always call yourself recursively. If binary search always calls binary search, this can't go on forever. Somebody eventually has to determine an answer, and that's what these two lines, either a positive answer, we found it, or a negative answer, you've looked, and eventually these things have crossed each other, and we were unsuccessful in finding that target value. And we can run that. We can pull that up in Eclipse. Here's the binary search program, and we can give it a target value like 5. If we run it with 5, oops, we seem to be still running. Let's see if we can convince it to run binary search instead of whatever it was running. Alright, did it find 5 true? Yep. And how did it do it? It started at 0 to 10, midpoint was 5, then it halved the interval, went to 0 to 4, and then it went high, the high end of that interval, 3 to 4, and then it turned out 5 was at that midpoint of 3. So 0, 1, 2, 3, 5 is right there. If we run it for a different value like 6, is 6 in there? No. So 6 ended up being false. It searched from 0 to 10, then it went to the low end, 0 to 4, then it went up to 3 to 4. Alright, it didn't find it at 3, so then it went to 4 to 4. Was it at position 4? No. And then this is the point where things have kind of got wonky, and low is now greater than high, in which case that's the failure condition, and then the recursion stops, and we return failure. So it's a bit of a complicated algorithm, but it has a very nice and compact recursive solution, and that's what we like about recursion. Things to avoid. Whenever you make a recursive algorithm, some things can go wrong. One thing you want to avoid is missing a base case. Here is a factorial, and it looks nice. It has the sort of induction step. If you want the factorial of n, well, what's that? That's the factorial of n minus 1 times n. The problem is there's no base case. There's no 0 factorial equals 1 base case. And what the computer will end up doing is starting at, say, I don't know, n equals 5. What's the factorial of n equals 5? Well, 4 factorial times 5. And 4 factorial is 3 factorial, and 2 factorial, and 1 factorial, and 0 factorial, and negative 1 factorial, and negative 2 factorial. And this thing will just keep going and going and going with an n that gets more and more negative. That's a bad idea. Another bad idea is, this is not as obvious. There looks to be a base case. All right, we're repeatedly calling bad idea with something 1 plus the old number divided by 2 plus this, and there's no guarantee this is actually ever going to hit, n is actually ever going to reach 1. If you do something like this, what you're going to see is, well, you might think this just, has like like you've caused an infinite loop. The program just runs forever. In fact, it won't run forever. Memory is limited on your computer, and every time this factorial calls itself, it requires a little bit of memory. And if you do that for long enough, you'll get a nice little Stack Overflow runtime error. And this is typically what you're going to see. And we can go run it. Let's we can cause Factorial to Stack Overflow. Here's the proper Factorial with a base case. We'll just comment that out, and then let's run it. And we Stack Overflowed, and this is what you'll get. There's a huge long list of you have to scroll all the way to the top to see actually the exception Stack Overflow error. This is how many times it was calling itself, quite a few times before it eventually failed. That typically means you've missed out on a base case and you're not terminating. All recursion must at some point come to an end. So there's just a webcomic about recursion. So at some point you shouldn't be recursing anymore. You should always have a base case, and here's an example of something we don't actually know. This is an open problem in mathematics called the Collatz sequence, and it's a very simple process. So if somebody gives you an integer, if the integer is 1, then you're done. If the integer is even, divide by 2, and then keep going. If n is odd, multiply by 3 and add 2. So the even numbers get smaller, the odd numbers get a little bit bigger. These always seem to eventually reach 1 and then terminate, but this is unproven. If you write a recursive algorithm, and it's easy to do, here's a recursive algorithm that computes that. It prints out the current number. If it's equal to 1, then it's done. If it's even, so here's our idiom in computer science for testing if an integer is even, n%2 = 0. If it's even, call yourself on n divided by 2, otherwise call yourself on 3 times n plus 1. And we can run it. Here's the same program in Eclipse. Alright, and we can put a number in here like 1, 2, 3, 4, 5, 6, 7, and then run it. And you can actually see it took that number, multiplied by 3 and added 1, then divided by 2, and so on, and it kept doing it and kept doing it and kept doing it, and then eventually it reached 1. And you can play around with that and see how long we can do another one. We can make it even bigger. 890. Alright, and that one took 351 steps, but eventually also went down to 0. We don't know if this always terminates. It seems like it does, but it's been unproven. And here's another webcomic about this Collatz conjecture. Let's switch gears for a minute and let's talk about graphics. And here are some recursive graphics. So this is something I did a while ago. I've got little recursive circles inside of other circles. But let's look at maybe something a little simpler. Here's a recursive graphic. This may look like it's very complicated to draw, but it's actually really easy. I can show you the code to draw this and many images like this on a single slide. And you can kind of see the recursive structure, right? We've got the H, big H, and at the point of the big H, we've got some medium-sized H's, and at the point of each of those medium-sized H's, we've got smaller H's, and so on. And here is the algorithm for drawing that H tree. For an H tree of order n, you start by drawing an H, and we're going to call the size to be, how long each the horizontal and the vertical sides of the H are. And then at each tip of that H, you're going to draw another H at half the size. And then at each of these H's, you're going to draw another H at half the size. And you're going to keep repeating until n reaches 0. And here's the program I promised that more or less fits on a single slide. You read in an integer from the command line and then call yourself, and we start off at a length of 0.5, That's the first argument, the size, and then we start at an x and y of 0.5. Okay? And let's see, where is it gone in the, there it is, H tree. And I got to move the window over for you so you can see it. Here's an H tree at 4. And we can increase it up to, let's go up to 6. Oh, and you can see it drawn. There's an H tree at 6. And here's an H tree at 7. And you can kind of see how the recursion's going. You can see it's starting in the upper left and then upper right, then lower left and lower right, and it starts with the big one but then works its way all down to the small one. And that complicated graphic is produced by this simple code, and you know, we don't need to look at the exact details, but you can see here we're calculating sort of the endpoints of those H's and then drawing the 3 lines required by the H. Then we call ourselves recursively 4 times. So there's no reason you always have to call yourself once in a recursive algorithm. Sometimes you do. Other times, like in the H tree, you're calling yourself 4 separate times recursively, and then each of those calls itself 4 times recursively. Finally, here's another famous number sequence, the Fibonacci number. Fibonacci numbers are defined by 2 base cases. Fibonacci 0 is 0, Fibonacci 1 is 1. And how do you find the next Fibonacci number? Well, you always just sum the 2 before it. So if you sum 0 and 1, you get 1. If you sum 1 and 1, you get 2. If you sum 1 and 2, you get 3. 2 and 3, you get 5. 3 and 5, you get 8, and so on. And it occurs in, you know, things in nature like this this little flowering head over here. And you might think, I mean, you've got this very natural recursive to calculate the next Fibonacci number. You just need to know the 2 previous. And it could be a natural fit for recursion, and you can solve this problem recursively in a algorithm. Here's the Fibonacci recursively. If n equals 0, then you return 0. If it's 1, you return 1. Otherwise, you return the Fibonacci of the 2 prior numbers. And you just keep calling yourself recursively until you reach those base cases. This is completely correct and works. It's compact and it's elegant. But there's a bit of a fly in the ointment, so to speak. If I were to compute the Fibonacci numbers using this recursive algorithm and measure the time, and I did. Here's the time I measured on a modern desktop or laptop computer. At first it starts out quite nicely. It's not taking any time at all, but as I crank up the size of Fibonacci number I want, something alarming happens. The time it takes to calculate keeps almost doubling. By the time I get up to 50, it's taken me over you know, almost a minute and a half to compute that Fibonacci number. If you think about what's happening in that recursive algorithm, when you try and compute, say, the Fibonacci 4, that algorithm's got to compute the Fibonacci of 3 and 2. That call to Fibonacci 3, well, what does it call? It calls the it asks for, please add the Fibonacci 2 plus the Fibonacci 1, and so on. You can see in this diagram, a lot of calculations are being repeated in this algorithm, and that's sort of the bad news in this algorithm. This thing is growing exponentially. Every time we increase this Fibonacci number by 1, it's taking about twice as long to do the calculation. And this is extraordinarily bad for computer science. Algorithms that grow exponential are really bad news. You can't solve very big problems if increasing the problem size by 1 doubles the amount of computation required. So can we not compute Fibonacci numbers? No, we can, and there's a simple way to do it. instead of this recursive algorithm, you can just keep track of the last two numbers. If you start two numbers off at 0 and 1, you can sum them together and realize the next Fibonacci number is 1. Then keep track of those two numbers and realize the next Fibonacci number is 2, and so on. And here is an algorithm that does it this way. It just has two local variables, n1 and n2, to track the last two Fibonacci numbers. We initialize to the base cases of the Fibonacci sequence, and then we just keep going until we've reached the target value, keeping track of those last two numbers as we go along. And if you were to measure the time of this, and I did, it's, you know, ridiculous. I can compute the Fibonacci number of 160 million in, you know, less than a tenth of a second. All right, and then of course this number was gigantic, and it was, you know, much bigger than these data types actually could hold. But for sake of example, even if you could compute such a big number, it takes virtually no time. This algorithm goes as the number n, and does not grow exponentially in the number n, and that's a massive difference in performance. To summarize, we looked at a very powerful concept in computer science called recursion. It's when a method calls itself. It's a little confusing at first, but once you get your head around it, it provides you access to elegant and easy to understand algorithms. You must be careful, of course, when you use recursion. You must be sure you always have base cases. Recursion must at some point come to an end. If it doesn't, you're going to get this stack overflow problem. And I would encourage you to kind of look at the examples in this lecture and try and sort out for yourself and trace the execution and try and learn how the computer is keeping track of things and calling itself and tracking its state and then backing itself out. So it's a good experience to run some of these algorithms so you can sort of start to learn how recursion works.